Good afternoon. Today I'm going to this device I'm talking about is based on the work in this previous year, and it's called charge or organic light emitting diodes. But it's basically still OLED, but it has some charge behavior. And so for the beginning, this is the technology called OLED. And I don't know, because it seems to be quite new and not many people knows, like if we were talking about 5 years ago. But I think now many people has already know what it is, so I'm not going to talk about a long introduction about it. But first of all, this technology is the application of it is to make a display or light source. And the display it make is a flat display. Basically, it's just like LCD. And this month, Sony has already have the first commercial OLED television, which is 11 inches screen and on sale. The thickness of the display is only 0.3 centimeter, compared to this LCD screen, which is about 1 centimeter thick. It's very impressive. And this kind of thing, organic, it has a name of organic in it because it's something really, it has some structure look like this. Most of the small molecule we use in this field has structure like this stuff or this stuff, with a lot of like pi bonds, and these pi bonds standing on each of this carbon atom would overlap, so the electrons can go through this area. And then in the film, electrons can even hopping from one molecule to another molecule, so makes the whole film conductive. And so basically, because it's organic, or you can say it's plastic, so it's flexible. And it has a lower power consuming compared to LCD. And if anyone knows about the basis of LCD display, you will know that it's very waste of the energy, because if you want to see a red from LCD display, you basically filter all the other lights out and only get the red, because the backlight is white basically. So this is very power consuming. And for the OLED, because it's a LED, so if you need a red, you just emit red. And if you need blue, you emit blue. So this is very good. And lightweight. The reason it has a lighter weight is you can thinking about, for LCD, you always need a glass as the substrate. And the glass is not heavy if it's in this size, but if you make it bigger, the glass can be very heavy. But for this OLED, you can put it on the plastic substrate. So it's very light. So this is good about it. So this is a very simple structure for the conventional OLED device. And the blue one is in sequence is the electron transporting layer beside the cathode, and then is the hole blocking layer. And then the green one is the active layer, which emit light. And the next one is the electron blocking layer. And the next one is hole transporting layer, and then the anode. So you can see this is quite not very good for OLED, because it requires so many layers. At the beginning, people said sandwich structure, but this is already a jumbo sandwich structure. And people, in order to increase the efficiency, people adding layers like crazy. Some people make a 10-layer structure and have a very high efficiency, but 10 layers of the device is really nonsense if we are talking about the commercial stuff. So this is not good. But here I'm just showing the basic structure of it. So when you apply voltage, the holes just transfer from the anode, and the electron transfer from the cathode. But you see, in this animation, the hole goes to the active layer first, and then blocked by the hole blocking layer. Wait for the electron, which is very true in most of the case, because in most of the small molecule we use in this area, the hole has higher hole mobility than electron mobility. So this can be a problem because we always have a lot of hole current than electron current, but you need one electron and one hole to form an exciton and to emit light. So that's why people put more and more layer, because they just want to block the exceed carrier. Okay. So the material I'm going to talk about today is the charged OLED, which is with only one layer, and it has one and it's I can show you the animation and you know what it's talking about. When you apply voltage, the -1 is anion. The anion flow to the interface of the polymer and anode, and then this will reduce the energy gap for the hole injection, and also because this cathode side has more ions, more cation here, so this will reduce the energy gap for this as well. And this is very important to increase the efficiency for OLED, because for most of the stable metal can use as the cathode. For example, people use aluminum or silver, but they all have the Fermi level of about 4.2 electron volts. And so this will cause a pretty big energy gap for the Fermi level of the cathode and the LUMO of the small molecule. And for this kind of structure, it can reduce the energy gap. So it's very good. And also, it goes like this. And if you notice, I make the holes go faster as well, because this is the same true in most of the device. And so this is single layer PIN junction. It can not only reduce the energy gap for injection, it can also form something like potential well, because this electron here, it can block the electron, and this ion here can also block the holes, so to confine the exciton, or to confine the two species of carrier inside of the device. So in this research, we use all these 5 different kinds of iridium complex, which are synthesized by our chemistry department, Professor Martin Bryce's group. And anion for all the complex are PF6 minus. So the center one is the most basic one with, this has a complicated name, phenanthrolene. These are the phenanthrolene, and this is the 2-phenylpyridine, this one and this one. So this is the most basic one. And then they replace one of the carbon into sulfur, or add some more fluorine here. to try to change the energy gap between the LUMO and HOMO. Oh, and this is something called Pdot. This is what is used to as the whole injecting layer in the device, because people mostly use something called indium tin oxide, ITO, as the anode, transparent anode. And this kind of stuff has a very rough surface. So this Pdot is to spin coat on the anode to smoothen the surface. And this is the substrate we use for the experiment. This is the pattern of the anode. In this case, it's ITO. And this is the cathode. In my research, I use silver. And so first is the anode, and then you spin coat the small molecule or the polymer everywhere, and then you cap with the cathode. So this green area are the only active area that would emit light. So now, in order to prepare the sample, first we have to clean the substrate. And this is the thing we use. This is the ultrasonic bath. And this is for the UV ozone. And this is the small molecule thermal evaporator, which is Lasker one. And we use this to thermal evaporate small molecule or just the cathode. And this is the stuff we measure our sample. And we put our sample in this holder. This is the Luminance Meter. And here, inside of this box is a photodiode. And inside here is an Ocean Optic USP2000 spectrometer. And this box is the switcher to control which pixel light. And here is a motor here, so we can rotate the sample. Oh, the reason we need a photodiode here and a luminescence meter here is to calibrate our data from the reading of from the photodiode. So it's like we record one data from the photodiode and we rotate 180 degrees and to measure the brightness and then calibrate it. So this is the sequence to prepare the sample. First, we put all those iridium complex in acetone nitrile with a concentration of 1.5% by weight. This will make the film about 60 nanometer thick. And the glass substrate clean with the following chemicals. And then the substrate bake in the UV ozone box for 5 minutes in order to increase the work function for ITO to like 5.1 electron volts. Sorry. And then the Pdot is filtered, and then spin coat on the ITO, and then bake it. And then bake it for 4 hours in the vacuum of 1 to -2 mbar. This is to remove all the water in the Pdot, because water is very bad for OLED device. And then we will spin coat the iridium complex on the Pdot layer. And finally, we put the whole thing in the small molecule evaporator and then make the cathode. All the EL characteristics are measured in air, and we still don't have a good way to encapsulate it. So everything is open in air for now, which is quite sad. So for the first result, for this is the picture for this most basic material. You can see it's yellow, and then it has a lot of spots on it, but it's quite bright. And the black the black curve means the first round of the measurement. And then after measure it for about 5 minutes, 10 minutes, I turn it off for 60 minutes and measure it again, which is the red curve. You see, this is the charging time for the device, which apply only 5 volts. But you see, for the first 10 minutes, you see the light begin to grow gradually. But when you turn off for 1 minute, turn it on again, it immediately has the same brightness as you turn off, as when you turn off. So this is probably because all the minus one anion, because they go to the interface of the polymer and the anode. And when you turn it off, the time is not enough for it to go back to the original position. So still, most of them are accumulated at the interface. So when you turn it on, it still have the same effect when you charge it. And this green one is when you turn it off for 5 minutes. You see all these anions go back further, so the brightness is lower than you turn it off for 1 minute. And this is the luminescence efficiency, which is, if you can see it clearly, it's only 1 candela per amp, which is very low, very low. And the reason for the efficiency this low is because of the strange high current we got out of our device. So this part is we're still working on in how to reduce this dark current. Okay, so this is for another complex, which is orange. And it has similar behavior. The black one is the first round. And then we turn it off. You don't need that much time to charge it again. Means the anion still at the interface of metal and ITO and polymer. And this is the last one I'm going to show, is the blue one. It all has the same property, like when you turn it off for a while, can charge easily to get the same brightness. And for this one, the efficiency is even worse, 0.1 candela per amp. Okay, and also you can see the surface is still very rough. The reason for this is probably because all these film are spin coated, and usually people use conjugated polymer, which has a long chain, to spin coat and make the more homogeneous film. And maybe it's because this is small molecule, so when you spin coat it, it just couldn't make the film as good as big long chain polymer. So this is something interesting when we look at the IV curve after we charge it. And this is the data compare between this complex and this. The black one is the original complex, and the red one is this one with 2 fluorine ligands. And you can see, after charging them for 3 minutes, and measure the IV curve, you see there are a 2-step increase of the IV. Normally for the diode, you should only have one turn on voltage. Like the curve should look like this, but it has a 2-step. So we're thinking that maybe this first turn on is, okay, before 1 volts, it's still an insulator, right? And after that, because the ion, the PF6, begins to flow, so you feel the current at this time. But because this current is caused by the ion, so there is no light coming out. And after about 3 volts, there is another increase. This is the injecting from the cathode anode. So from here, we begin to see the light, and which is very true when we look at this other curve. This is the brightness against the current density. So you see before 4 milliamps per centimeter square, there's no light. And if you look at this figure, you see here is the point when you have 4 milliamps per centimeter square. So it's really that before this, there's no light coming out. But after this, you begin to see the light, which is proportional to the current. So this behavior, I think maybe in the future we can use this behavior to compare different complex, the ability, the mobility for this anion. So finally, we can look at all these 5 complexes we have, and we see them beautifully spread out in the EL spectrum figure. The yellow one is the original one, which is yellow, and then from the left to the right is from the bluest to the reddest. We can stop here and talk about why this molecule has different band gap. According to the calculation of the orbital, the calculation tells us that the HOMO is at this area, and the LUMO is on here. So the energy gap is this one, the yellow one. So when you add these two things here, it seems to push the LUMO higher, so make it green. And for this one, you put some fluorine here. And this fluorine will attract the electrons from this HOMO, so make the band gap wider, so it's more blue. And for this one, they put sulfur in it. And this sulfur has 2 electron pairs at here. So it supplies more electrons to the HOMO. So this might increase the HOMO, so make the band gap narrower, so make it red. And this one, it has a longer chain at the LUMO position, so this might reduce the energy as well. So also make the energy gap smaller. For the RGB point of view, we already have a green one. This one, number 9, is quite red, but this one, number 7, is still not blue enough. So the chemistry guy, they are still working on where they are going to try to put this stuff at here and see whether we can get a real blue one, which is about 470 nanometer. And I was just talking about the low efficiency comes from the strangely high current. And this one was what we get at the beginning of this year. And this is the molecule we tried. And with this one, because we made the film thick enough, maybe this will reduce the effect of the short circuit. So this one we get a pretty good brightness and efficiency as high as 7.8 candela per amp. But because the film is thicker, so it requires longer time of charging. You see, we're talking about something like 30 minutes. But for my previous device here, only requires like 3 minutes or so. So here comes the conclusion. This is something has the potentially high efficiency at low voltage. Maybe it can as low as 3 volts or less, smaller than that. But this dark current we have to remove to make the efficiency high. And also it's color tunable, because you see we can do a lot of things in these ligands or put something here, so and to affect the spectrum, the EL. And then because it's spin coating, it's not, although it's more molecule, but it's not thermal evaporated, like 10 layers. No, this is only one layer. So this is very good. This is the benefit for this material. And everything is not, it's just doing in air, not the vacuum. And the charge time has to be improved because no one can tolerate that you go into the house and turn on the light, you wait for 10 minutes to see anything. And then the lifetime, you see all those spots. We have to try to figure out where that comes from and to improve the device lifetime. Maybe if we find a way to encapsulate it, and if the lifetime immediately improve. And also, as I mentioned before, because the holes are usually more than electrons in the device, so we have to improve the balance for both carrier. And then I have to thank Martin Price to synthesize all the material for us. And Andy always give me very helpful suggestion. And finally, Dr. Ben Lyons, he is very helpful in solving practical problems in experiment. And also he teach me English with his very fluently Chinese. So that's it. Thank you.
Thanks very much. Time for a few questions, I think.
When you had these sort of the charging times, it looked like some of them charged and then became more luminous, and then after a little while, not the yellow, but the orange and the blue, and particularly the blue, sort of seemed to come down in brightness after a period of time.
Like this one, right?
Yeah. Do you know why that is?
Yeah, you mean this, right?
Yes.
I think this is because as I mentioned, the device is not encapsulated, so the measurement is just measured in air. So maybe this is because the molecule react with the waters or oxygens in air, and then degrade. Maybe this is because of it.